Hi friends, good morning. Today we are going to start with a new topic, that is Laplace transform. Okay. In the last lecture we have seen Fourier transform, and Fourier transform that we have represented as f of s is equal to minus infinity to infinity, that is f of t e raised to minus I omega t, right? E raised to minus I omega t, and we have some constant here, normalization, that is root 2 by pi, right? So this is the Fourier transform that we have studied, right? And here we have discussed as it is the integral expansion of Fourier series, right? When we consider the Fourier series, that is f of t is equal to a0 by 2 plus sigma n is equal to 1 to infinity an cos n x plus sigma n is equal to 1 to infinity an sin n x. So here when we consider this summation, this x can take the discrete values only. So when we turn it into its integral version, so it can take a continuous value. So and also we have discussed some graph like this. Okay, so it is turned into integration, then the shape of this graph changer to it can take continuous value like this, right? So it become a closely packed structure, that all we have seen there. And here this Laplace transform is defined in the 0 to infinity interval, not it is from minus infinity to infinity. Okay, this is varying from 0 to infinity, and this condition t is always greater than 0. Okay, it is this Laplace transform is the integral expansion of Taylor series. This is integral expansion of Taylor series. Okay, so this is the integral expansion of Taylor series. What is Taylor series? That we will discuss in complex analysis, that we will take after this Laplace transform. Okay, so it is the integral expansion of Taylor series. Okay, so here the value is taken always positive, so that's why we are considered 0 to infinity integral here. And also here this Laplace f f of t, yes, okay, Laplace fs is defined by integral 0 to infinity e raised to minus st f of t dt. Okay, so here instead of this s, we have used I omega. In Fourier transform we have used the I omega. This s may be complex or real function. Okay, s may be complex or real value, and t is always greater than 0. Okay, now see, so integral 0 to infinity e raised to minus st f of t dt is the general expression for this Laplace transform. Now if you have a function e raised to, what is the Laplace transform of t? Okay, so we can replace this f of t with t. Okay, or Laplace of we can see Laplace of 1 first. Okay, what is Laplace of 1? That is integral 0 to infinity e raised to minus st. This Laplace of 1 means f of t is equal to 1, that is f of t is equal to 1 means dt. So e raised to minus st on integration, that is e raised to minus st divided by minus s. Okay, integral 0 to infinity. So when I am substituting upper limit minus lower limit, that is e raised to minus t changes to infinity. So e raised to minus infinity divided by, so this minus 1 by s I can take out, and e raised to 0, that is minus 1 by s. E raised to minus infinity is 0, e raised to 0 is 1, so this is equal to 1 by s. So e raised to Laplace of 1 is 1 by s. Okay, now let us find what is Laplace of t. Okay, what is Laplace of t? Okay, so we have seen what is Laplace of 1. Now we can see what is Laplace of 1. Let me go to the blackboard, right? So to find Laplace of 1, Laplace of t, See, my expression is integral 0 to infinity, that is e raised to minus st f of t dt, that is t. Okay, t dt. Now we can integrate this by parts. So first function into, okay, integral of second, right, is e raised to minus st divided by minus s, right, minus what is integral of first. Integral of first is, that is differential of first into d by dt of integration by parts into t, integral e raised to minus st dt. Okay, all dt. Okay, so I applied the parts, and finally we have to give this limit 0 to infinity. So when I am giving the limit e raised to minus st by minus s 0 to infinity, and here this is 1, here again e raised to minus st by minus s, so this I can write as minus 1 by s here, right, and again if it is I am doing, again I have a minus 1 by s e raised to minus st, right. So this is the final expression that I got, and when I am substituting this infinity value, this part will be 0. When I am substituting 0, this part will be 0. So we have only this term. Okay, so we have only this term 0 to infinity. Okay, so I can substitute this value, that is 1 by s square, and I minus here, this minus minus cancel, and if I am substituting here minus infinity, that is e raised to minus infinity minus e raised to 0. This part is 0, e raised to 0 is 1, so answer is 1 by s square. Okay, now if you do Laplace of t raised to 1 in the same format, you will get Laplace of t square, you will get 2 divided by s cube. If you do Laplace of t cube using this parts method, you will get 6 divided by s raised to 4. Okay, so generally you can write Laplace of t raised to n is equal to n factorial divided by s raised to n plus 1. Okay, so when n is equal to 3, that is 3 factorial, that is 6. Okay, 3 plus 1, that is 4. Okay, so Laplace of t raised to n you can generally express as n factorial divided by s raised to n plus 1. Okay, now let us start with another function, Laplace of e raised to at. Laplace of e raised to at. Okay, so what is Laplace of e raised to at is integral 0 to infinity e raised to minus st f of t dt. F of t you have to replace with e raised to at dt. Okay, that is equal to integral 0 to infinity. This I can write as e raised to a minus s, right, a minus s t dt. Okay, now here this value is defined from 0 to infinity, right. So when I am integrating this, what I get, that is e raised to a minus s, right, divided by a minus s. Okay, all raised to 0 to, that is limit is varying from 0 to infinity. Okay, here I have a t. Now if you look to this term, when I am substituting here, this t is equal to infinity. Okay, when I am substituting t is equal to infinity, what about this e raised to infinity? E raised to infinity is, that is not equal to 0, that is some quantity, right. Okay, that is some quantity, e raised to infinity divided by this. So this term is inconsistent here. Okay, if this, so this can be defined only when s is greater than 0. Okay, if s is greater than 0, so s is greater than 0, then what I can say, otherwise its value will be infinity. E raised to infinity is infinity, e raised to infinity is infinity, so answer will be infinity. Okay, Laplace transform of a function e raised to at that is equal to infinity means it is divergent. Okay, for example, we have an example, we can take an example of divergent function. See, suppose if you draw the tan x graph. Okay, here f of x is equal to tan x and here is the function pi by 2. So tan x value is increasing, tan 0 is 0. Okay, tan 45 is 1. Okay, what is tan pi by 2? Tan pi by 2 is infinity, so it will go to infinity. That means it is divergent. Okay, so Laplace of e raised to at, suppose you imagine s is greater than a. Okay, so here in Laplace transform of e raised to some coefficient into time, so here this s must be greater than a, then only the function is convergent. Convergent means if I substitute this, look here, if s is greater than a, so I can write this expression as e raised to s minus a, right? S minus a, I can take a negative out into t divided by, here also I can take if s is greater. Okay, here also I have taken a negative out. Then if I am substituting the limit, right, then when I am substituting this infinity, that is e raised to minus infinity. Okay, if s is greater than a, so e raised to minus infinity, that is will be 0. Here I have outside I have one minus of s minus a. Okay, I have taken this minus s minus a out, and when I am substituting this infinity, this become e raised to minus infinity, that will be 0, right? And when I am substituting this t is equal to 0, that is e raised to 0, that is 1, so this will be 1 by s minus a. Okay, so this is the e raised to at. In the similar way, you can prove e raised to minus at. Suppose if you are substituting this similar way, you can substitute this as e raised to minus at. If you Laplace of e raised to at, that is equal to 1 by s minus a. Now if you are finding Laplace of e raised to minus at, then the sign of the a will change here. Okay, that is 1 by s minus minus a, that is 1 by s plus a. Okay, so these are the important result. Okay, so similar way, we can solve all the fundamental quantities Laplace transform like t, t square, t cube, e raised to at. Okay, so based on that, by calculation we have lot of basic results. Okay, so let us go to the basic result. Okay, if Laplace of b, yes, so b you can take. Okay, then remaining quantity Laplace of first quantity, Laplace of 1. Okay, what is Laplace of 1? 1 by s. So b into 1 by s, that is b by s. This all we have discussed. Okay, so here Laplace of t, that also we have solved, that is 1 by s square. Okay, these all are possible only when s is greater than 0. If s is already negative here and here also a negative, so then it is positive, then e raised to infinity will come, then answer will be infinity, that is divergent condition. Okay, so to get convergent quantity, okay, we must take s is greater than 0, that we have already discussed. Now to solve Laplace of cos omega t. Okay, so this is a function Laplace of cos omega t. What we have to do is, we are writing this cos omega t as e raised to I omega t plus e raised to minus I omega t by 2. Okay, so to do, we can go to the blackboard. So Laplace of cos omega t. Okay, Laplace of cos omega t. So what I can write, this is Laplace of that is integral 0 to infinity e raised to minus st f of t. F of t is cos omega t. Now I am going to replace this cos omega t. Cos omega t is e raised to I omega t plus e raised to minus I omega t divided by 2. So this is the cos omega t exponential representation. If I am substituting this value here, So what I can write? This is e raised to I omega t plus e raised to minus I omega t divided by 2. Okay. Okay. Now see here, I can expand this bracket. I can take 1 by 2 out, 0 to infinity, and here this I can take as, so this 1 by 2 I can take as common, and this is e raised to, see, this is I omega minus s. Okay, if s is greater than I omega, so I can take a minus out. This is s minus I omega into t. Okay, plus here this is minus, so s plus I omega, so e raised to minus s plus I omega, right, into t. Okay, now dt. Now when I am integrating and substituting the limit, what I can write, this is 1 by 2 into, here I can write this as 1 by s minus I omega, right? Okay, so you may write this as minus 1 by c omega, and when I am integrating, I am getting same function, that is s minus I omega. Okay, integration process is over, and I can substitute 0 to infinity, plus here also when I am integrating exponential function, I am getting the same function, e raised to minus s plus I omega, right, into t divided by, so I have to we have to divide with its differential, that is minus s plus I omega, and then we have to substitute the limit. Okay, now if you look to this, that is 1 by 2 into, if I am substituting, when I am substituting t is equal to infinity, this part will be 0, e raised to minus infinity is 0, so I can write this as 0 minus, okay, and this as minus, and here when I am substituting 0 1, so here I have another negative sign, s minus I omega, right, and here similarly I can write as 0 minus minus 1 by s plus I omega. Okay, so this is equal to 1 by 2 into 1 by s plus I omega, 1 by s minus I omega, right, plus 1 by s plus I omega. Okay, so when I am crossing this half into, so when I am crossing this, I will get 2s divided by s square plus omega square. Okay, s minus I omega into s plus I omega, that is s square plus I omega the whole square, but this s square minus I omega the whole square, I square is minus 1, so this will be 2 cancel. So Laplace of cos at is equal to s by s square plus omega square, and Laplace of sin at similarly you can derive as s by s, not s, it is a divided by s square minus omega square. Okay, so a by s square plus omega square, and a by s square minus omega square. Okay, these are the result. So let me check the sin at result and cos at results in the main board. Okay, so let me go to the main board and check the various result. Okay, so okay, here also plus. Okay, only change is this is a by s square plus omega square. Okay, so based on the discussion, we can express results based on this. Okay, these all are the fundamental results which we have by heart. Okay, so what are the result? Laplace of 1 is 1 by s. Okay, what is Laplace of t raised to n? That is n factorial divided by s raised to n plus 1. What is Laplace of e raised to minus at? That is 1 by s plus a. This all we have done. What is Laplace of e raised to at? 1 by s minus a. What is Laplace of sin at? That is a by s square plus a square. What is Laplace of cos at? S by s square plus a square. In a similar format, Laplace of sin h at, you will get a by s square minus a square, and cos h at s by s square minus a square. This derivation we need not. If you are interested, you can derive. It is in the way by substituting the sin h at, you can write as e raised to x minus e raised to minus x by 2. Okay, then you can substitute in the ordinary form and you can derive like this. Okay, so sin h at is equal to a by s square minus a square, and cos h at is s by s square minus a square. Okay, similarly, Laplace of root t is equal to root pi divided by 2s raised to 3 by 2, and Laplace of 1 by root t is equal to root pi by s. Okay, so these all are the fundamental result which you have to by heart to do the problem sections. Okay, so these all result you have to by heart. Okay, now based on certain properties, in the next class we will discuss some properties of this Laplace transform. Based on that we can derive the Laplace transform of different complicated functions. Okay, so this all about today class, and we can see in the next class. Okay, thank you.